Okay, guys, so we discussed closed and manometers and open end manometers in the last lecture, so we'll be continuing on seeing that. Okay, so let's get started first with the closed end manometer. Okay, so suppose we have the apparatus setup like this is the gas chamber, and on this gas chamber we have this closed end tube which is filled with vacuum and mercury. Okay, so what will happen is this gas will exert some pressure on this mercury. As a result, let's say this was point X and this was point Y. The point Y raises itself to let's say height of L because of the pressure applied by the gas on the mercury. So we'll say that pressure of point X and pressure of point Y in the mercury would be the same. Okay, and pressure of 0.5 would, we can say that pressure of 0.5 would be nothing but the pressure exerted by this height of mercury. Okay, so which is nothing but, I'm just writing P of L, which is the height of mercury raised in the beaker or in the closed manometer. Okay, so pressure of gas would be also equal to that. Why? Because pressure of point Y is equal to pressure at point X, and pressure at point X is exerted by the gas here. Okay, so we'll write that P of Hg is in terms of height of mercury. Okay, so let's say for an example, the height of the mercury raised from point Y was 7.6 centimeter. So then we can write that pressure of gas at point X would be 76 centimeter of Hg or 0.1 atm. Okay, so we can say that pressure of gas is pressure of mercury or the height of mercury raised. Okay, and that would be equal to pressure of mercury at point Y, which is nothing but pressure of gas at point X. Okay, so that is 0.1 atm. I'm directly writing here that it is 0.1 atm. 0.1 atm. Okay, similarly, if height was 15.2 centimeter, let's say, then pressure of gas will be equal to pressure of gas at point X would be equal to pressure of mercury at point Y, which should be equal to 15.2 divided by 76, which is nothing but 0.2 atm. Okay, so now let's see and move on to closed end manometers, or rather open end manometers. Okay, so we'll be seeing open end manometers now. Okay, so in open end manometers, let's say again we have the same apparatus in which we have a gas chamber. Okay, and this gas chamber is filled with some gas here. Okay, after filling the chamber, it is getting disclosed. Okay, and this is further set up into a manometer tube, a manometer apparatus, which is open end. Okay, open into the atmosphere is open end manometer. Okay, so this is open so that air from the atmosphere can come in. So let's suppose this was the level of mercury, this was point X and this was point Y, and gas will also exert some of the pressure on the mercury. So let me first fill out the mercury. So this is the mercury, and this is open air. Okay, and this is the pressure of gas which is exerted on the surface of mercury at point X. So this is P of gas, this is P of gas exerted. So let's say if the height of the mercury at point X and point Y are same, okay, or we can say that both are leveled up, then we can say that. And by the way, what is the pressure of mercury, or rather what is the pressure at point Y of mercury? So pressure would be 1 atm. Why? Because atmosphere is there, or rather air is filled up in the manometer apparatus, so it would be exerting P of air, which is 1 atm. So since P of X would be equal to P of Y, this implies P of X, which is equal to P of gas, which is simply pressure exerted by gas molecules on the surface X, would be equals to 1 atm. Okay, this was the case when the height of both the x and y remains the same. Now what happens is, what would be the what would be the uh, pressure exerted by the gas when we have something like this, that x point comes here, or its height increases to this point and y is still here. So this implies that, let's suppose this was point x dash. So now this was the case 1. Now in this case 2 which we are looking at, case 2 is p of x dash should be equals to p of y, which is equal to 180 m. And we also know that p of x dash is p of gas plus this height L of the mercury raised here. Okay, so this would be equal to uh, rho g L. Rho is the density of mercury, okay, and obviously we know that how is this rho gl term coming into the picture. We know that pressure equals to force per unit area. Force is the m into g. M is the mass of this height L of mercury divided by cross section area of the manometer tube, cross section area of the manometer. So m can be written as density of mercury times volume of mercury in that L height times g divided by cross section area of the tube, and volume of mercury can be written as cross section area times the height, which is L, times g divided by A. Hence we can write that pressure will be equal to rho g L. Okay, so pressure here at point x dash would be pressure of gas which is exerted here plus pressure due to this L part of mercury. Hence pressure of x dash would be P of gas plus rho gl, and we equate it to P of gas. So we equate it to P of y. So pressure of gas plus rho gl would be equals to 180 m. So from this, pressure of gas can be calculated as 1 minus rho gl. Okay, so this was second case, and we can have one more case in which we have something like in this case x is not rising. In fact, what is happening to y is actually getting raised up and up till here. So this becomes y dash and y point is here. Okay, so in this case what can we comment on the pressure of gas here. So pressure of gas here would be, or rather pressure of gas would be at pressure of point x dash, and pressure at point x dash would be pressure at point y dash. Okay, because they both belongs to the same height, and pressure of y dash can indeed be written as pressure at point y plus, let's suppose now this is height L, so pressure at y dash would be pressure at point y plus rho g L, and pressure of y would be nothing but equals to pressure of air, P of air, which is nothing but 180 m. So we can find it here that P of gas would be 1 plus rho gl in the third case. Okay, so just other not an example, let's directly look into a new concept where we have two immiscible liquids. Okay, so in two immiscible liquids, let's suppose we have a beaker and we have two immiscible liquids in it, and we have to determine what is the pressure at various points, which I'm just trying, or which I'm just marking. So we have to find the pressure at this point, which is 1, pressure at this point, which is 2, and pressure at this point, which is 3. So we have to find the pressure at respective points. So this is height h1, this is height h2, this is liquid A, this is liquid B, both are immiscible. Okay, so what is the pressure at point A? So pressure at point A, or rather pressure at point P1, pressure at point 1 would be nothing but ATM pressure, which is nothing but 1 atm. What is pressure at point 2? Pressure at point 2 would be pressure at point 1 plus rho A, which is density of liquid A, G into H of A. Let's say this is HA and HB. This is height A, HA, and this is HB. Okay, so now it would be something like P1 plus rho A G HA, and what would be pressure at point 3? Pressure at point 3 would be pressure of point 2 plus rho B G HB, which can be further simplified into what is P2. P2 is P1 plus rho A G HA plus rho B G HB. So this would be pressure at point 3. Okay, just adding the pressures here to calculate what is the pressure at different points in the vessel. Okay, so now what happens if we have two miscible liquids? Okay, so what happens here is, so suppose we have this solution. Okay, this solution contains two liquids. Let's suppose liquid A and liquid B. Okay, and before going into further calculation, let me first write that how is this miscible liquid formed. So this beaker initially had two partitions. This was the initial state and this is the final state. In initial state, what the beaker had was, we had solution A and solution B, or rather liquid A and liquid B. So upper part was liquid A and lower part was liquid B. So this was liquid A and this was liquid B, and it had partition between them, or you can say there was a vacuum here. Okay, now what happened is, we removed these two partitions. As a result, so initially it was having height h1 and it was having height, let's say, h2. Okay, and density was rho1 for liquid A and rho2 for liquid B. Now what happened is, remove the partition, and this is the final state where liquid A and liquid B are miscible and cannot be differentiated. Now we want to calculate the, this is suppose height h by 2. H is a total height, pressure at point 2 and pressure at point 3. Okay, so again pressure at point 1 would be pressure of ATM, as air is present here, which would be nothing but 1 atm. What about P2? P2 would be nothing but pressure at point 1 plus rho of the resultant solution G into H by 2. Okay, and P3 would be nothing but P2 plus rho of solution G again H by 2, where rho solution is the density of resultant solution. Density of resultant solution. Okay, and how do we calculate rho of solution? Rho of solution would be simple, mass of total solution, total mass of solution rather, divided by total volume of solution. What is total mass? Total mass would be nothing but density, or rather mass of A plus mass of B, and volume of solution would be again volume of A plus volume of B. We can write for mass of A as nothing but density of A times volume of A, plus mass of B would be density of B times volume of B, which was initially mixed to form the final mixture, divided by volume of A plus volume of B. As we can see that rho of A times volume of A would be nothing but cross section area of the beaker, which is A, times h1, which is the height of solution A, initial height of solution A was H1 and initial height of solution B or liquid B was H2. So rho B times cross section area of the beaker times what would be the height of B which was taken, it was H2, again divided by volume of A would be again AH1, volume of B would be AH2. We can cancel A from all the terms from numerator and denominator. Finally volume of, or rather density of solution would be density of A times H of A or H1 plus density of B times H2 divided by H1 plus H2. Okay, so this is the density of solution. Once we know what is the density of A and what is the height of liquid A and B which were used to have the final mixture, then we know the density of solution. Okay, and once we know the density of solution, using the same density of solution, we can put that value here and we can know the P2 and P3. So with this we come to the end of this lecture. In the next lecture onwards we will be seeing very important concept which are gas laws. So till then, good luck and goodbye.